Welcome to The Explainer. Today, we're going to crack the code on a single, tiny symbol that's at the very heart of digital privacy. It's a symbol that basically determines how safe your personal data really is.
To really get why we need a new kind of privacy, you kind of have to start with a history of failure. So let's rewind to 2006. Both AOL and Netflix had these massive privacy disasters. See, they released huge datasets they thought were anonymized, but it took researchers no time at all to prove that by linking that data with other public info, they could figure out who was who. The lesson was learned the hard way. Just stripping out names? Yeah, that's not even close to being enough.
And this just throws up a massive question for our digital age, right? We want to learn from all this data, for medical breakthroughs, for social science, for just building better tech. But how do we do that without putting the very people we're trying to study under a microscope?
Well, the answer, as it turns out, comes from a really powerful mathematical concept. It's called differential privacy. The best way to think about it is like a formal, provable guarantee, almost like a magical shield that protects the secrets buried inside a dataset.
Okay, so the core idea here is to give you what's called plausible deniability. The results from the data are intentionally blurred, just a tiny bit, so that anyone looking at them can never be 100% sure if your specific information was even used in the first place. You're perfectly hidden in the crowd.
So how do they actually do that? Well, a really common method is something called the Laplace mechanism. It takes the real, true answer to a question and adds a little bit of carefully calculated random noise. You can see it on the slide here. This noise creates these overlapping probability curves. It's just enough of a blur to hide any one person's data, while the overall result is still accurate enough to be useful.
But here's the catch. This privacy shield isn't just a simple on or off switch. It's much more like a dimmer dial on a light, and it's controlled by one single, absolutely critical parameter that forces a really important choice.
And that parameter, that dial, is called Epsilon. Epsilon basically represents the entire privacy budget for any analysis. It's the number that puts a value on that fundamental trade-off between how private the data is and how accurate the results are going to be. Okay, let's break this down. A low epsilon means you're adding a lot of that noise we talked about. You get this incredibly strong privacy guarantee, a powerful shield. But the downside is your results are less accurate, kind of fuzzy. On the flip side, a high epsilon means you add less noise. You get much more accurate results, but you guessed it, the privacy shield gets a whole lot weaker.
But here's the real puzzle. These are just abstract numbers. In the real world, data scientists have used epsilons from as low as 0.01 to as high as 7. But what does that actually mean for you or me? How do we take this Greek letter and turn it into something that tells us how much risk we're really facing?
To crack this code, researchers have come up with two really powerful ways to think about epsilon. The first is based on a worst-case risk assessment, and the second is based on thinking about it like an economic bargain. Let's start with the first one.
Okay, so for this first method, we have to put on our black hat. We're going to think like the adversary. We're going to imagine the absolute worst possible scenario and figure out the maximum risk a single person could ever face by being in a study.
So let's play this out with a story. Imagine a school surveys students about drug use and then publishes the results with differential privacy. Now, our adversary, we'll call her Eve, knows almost everything about her son's classmates. She wants to use this published data to figure out if one specific student is a drug user. Epsilon is the one thing that limits how much more certain she can become.
Now, here's what's so fascinating about how this works. The risk to any one person isn't fixed. As you can see here, when more people join a study, when N gets bigger, the privacy risk for any single one of them actually goes down. Why? Because your personal data just has a much smaller effect on the final outcome when you're 1 in 1,000 versus 1 in 10.
This whole way of thinking leads us to this really handy concept called the global privacy leak, or gamma. It's basically a tool that measures the adversary's maximum possible gain in knowledge. It gives us a number for how much more certain Eve can become about you, turning what was a 50-50 guess into something much, much more confident.
And this graph shows it perfectly. It plots that privacy leak, gamma, against epsilon. Now, if you follow that curve, you can see that for an epsilon right around 1.1, which is the natural log of 3, the global privacy leak is 0.5. What that means in plain English is that Eve can become 50% more certain about which students use drugs. This is how we make that abstract number feel real.
And this table is where the rubber really meets the road. It takes all that theory and gives us cold, hard numbers. Look at the worst-case risk, where Eve knows it's either you or just one other person. With an epsilon of ln3, her chance of guessing right jumps to 75%.
But look what happens in a more realistic group of 100 people. That same epsilon adds a risk of just under 3%. That's a huge difference.
So probably the best way to think about this is like the chance of rain in a weather forecast. It's not telling you that it's definitely going to rain on your privacy, but it does give you a really clear probability-based understanding of the risk you're taking on.
Okay, but risk isn't just about the math, right? It's also a social question, an economic question. And that brings us to the second, totally different way of understanding epsilon. And this isn't just my opinion. The legendary Cynthia Dwork, one of the pioneers who helped invent this stuff, she put it perfectly. Choosing the right value for epsilon isn't just a job for the techies. It's a social question. It affects every single one of us.
So let's put on a different hat now. Let's stop thinking like a spy and start thinking like an economist. We can actually look at epsilon as the result of a negotiation, an economic bargain. On one side of the table, you have the data analyst. They need the highest accuracy possible to get useful, meaningful results. On the other side, you have the participant, that's you and me, who's taking on a risk by sharing data and want it to be worth it. Epsilon is the balancing point. It's the number where the analyst gets enough accuracy and the participant feels the risk is low enough for the reward.
So when you put these two ideas together, the worst-case risk and the economic bargain, you start to see that setting this privacy power dial isn't really about the math at all. It's about deciding, as a society, what kind of balance we want to strike.
So, let's bring it all home. We started by seeing how simple anonymization is just broken. Differential privacy gives us a real, provable, mathematical shield. Epsilon is the dial that controls how strong that shield is. And by learning how to translate that dial into real-world risks and economic trade-offs, we can see that choosing the right epsilon isn't a technical problem. It's an ethical and social choice about the value we place on both discovery and privacy.
And that leaves us with a final, huge question to chew on. In this age of big data, where the potential for discovery is just unbelievable, what is the right balance? How much risk are we, as a society, willing to accept for the reward of discovery? And maybe the most important question of all is, who gets to decide?